And if we know the optimal solution of the primal problem, we can find the optimal solution of the dual problem or the vice versa. Now to do that, we have already done two methods. One is with the help of CB transpose B inverse. We have already done method 1. And the second method by directly reading the dual variable from Zj minus Cj given in the optimal table of the primal problem. And now we'll see how this third method works, which is complementary slackness condition. So there are two conditions that we can apply in that, and then we can find the optimal solution. So the first condition says, in the optimal solution of the system, whichever system we are solving, currently let's say if we are solving the primal system, if the ith variable is strictly positive or it is a basic variable, then the corresponding ith constraint in dual problem is satisfied as an equality constraint. Or I can say ith constraint slack surplus variable is 0. So here in condition 1, if the original variable appear in the basis, then the corresponding slack surplus variable in the dual problem is 0. So this gives a relation between the original variable and slack variables. Condition 2, in the optimal solution of primal, if ith constraint is satisfied as strict inequality, then the corresponding ith variable of its dual vanishes or it becomes 0. Now let us see how these conditions are applied, and then we can come back to these conditions to explore them again. So let's take an example here. So take an example here. So I'm considering LPP. Let me to consider this as a primal LPP, which is given as maximization of Z equal to 4x1 plus 10x2, subject to constraints 2x1 plus x2 less than or equal to 50, 2x1 plus 5x2 less than or equal to 100, and the third constraint is 2x1 plus 3x2 is less than or equal to 19, and all my decision variables are non-negative. Now the question is, solve LPP using simplex method and find the optimal solution of dual using the optimal solution of primal by applying complementary slackness conditions. So if you want to apply the complementary slackness condition, then let's see how to solve this problem. So for the optimal solution of this primal, I can use simplex method. So using simplex method, we can find the optimal solution of primal. So I'm not solving the whole problem, but here I'm only providing the last optimal simplex table of this given primal problem. So the optimal simplex table of this primal problem look like basic variable. So I'm writing optimal simplex table of primal is given below. So we have basic variables, we have Zj minus Cj, and here I'm writing the solutions So in the optimal simplex table, we see that x1, x2 and s3 appears in the basis, and here we have all the variables x1, x2, s1, s2, s3. As you can see that there are two variables in the primal problem. So we are solving this primal problem. There are two, and then there are three slack variables that will appear in these three constraints. So we can see that once you solve this LPP, you will find these entries. Now these are basic variables, so we have these entries 1, 0, 0, and these are obtained by using standard row operations and by using normal simplex algorithm. Okay, so from here you can read the optimal simplex solution. So what is the optimal solution of primal? Now, because in the primal we have the problem as maximize z, so we have maximum z, this is 200 at x1, x2, s1, s2, s3, and the solution of x1 is 150 by 8, x2 is 25 by 2, and s1 is a non-basic because it is not appearing in the table, s2 is also not appearing in the table, and s3 is 15. Now if you go back to the complementary slackness conditions, you see here the condition 1, it says you have to read the solutions from the optimal solution of the primal. So if the ith variable is strictly positive, or if it is a basic variable, so we need to identify which are the basic variable in the optimal table. Then the corresponding slack surplus variable are 0. So let's also write the first dual of this problem. The dual will be given as minimization of y. This is 50y1 plus 100y2 plus 90y3 subject to 2y1 plus 2y2 plus 2y3 greater than or equal to 4, y1 plus 5y2 plus 3y3 greater than or equal to 10, and all yi's are greater than or equal to 0. Now here and I can also write this into the equality system because we want to find the values for this corresponding slack variables also in the dual problem. So my equality constraints will look like, I'm writing s1 dash 4, this is minus because it is a surplus now in this case, so it is minus s1 dash, and the second constraint look like y1 plus 5y2 plus 3y3 minus s2 dash equal to 10, and then of course all variables are again greater than or equal to 0. Now we want to find the optimal solution of the dual. Optimal solution of dual. So in the dual we have the variable as y1, y2, y3, s1 dash and s2 dash. This is equal to, now you see here, if the original variable appear in the basis, so here which are appearing in the basis? x1, x2 and s3. These three are basic variables and these two are non-basic variables. So I should use some other color. Yes, so these two are non-basic variables. So from the basic variable we are going to write these values. So let's see this. So if I only look x1, x2, s1, S2, S3. Because S1 is a basic variable, so this means my corresponding S1 dash, this is 0. So this value means Y1, Y2, Y3, S1 dash and S2 dash. So S1 dash is 0. Because X2 is appearing in the basis, so the corresponding slack variable is 0. So this is value is 0. If there is some slack variable appearing in the basis, then the corresponding original variable. So if S3 is appearing in the basis, then Y3 will vanish. So Y3 means Y3 is 0. And now the only remaining left out is Y1, Y2. So we don't have any relation with Y1 and Y2. So the red line is due to the condition 1, and when we apply condition 2, so this is when S3 corresponds to Y3. So once you know that there are some variable in the dual which are already 0, now substitute star in equations delta. In delta we find after solving the system, after solving 2y1 plus 2y2 equal to 4 and y1 plus 5y2 equal to 10, because we see y3 is 0, s1 dash is 0 and s2 dash is 0. So you can simply solve this and we get what is the value for y1. y1 is your 0 and y2 is 2. So the whole system solution is, so optimal solution of dual is now 0, 2, 0, 0, 0. And if you substitute this in the objective function of the dual, we get here that the minimum of capital Y, which is we have, because we have selected here it as minimum of Y. So minimum of Y is nothing, but it is also 200. So that's how you can read the optimal solution of the dual. So what we want to say is, in the condition 1, if the original variable appear in the basis, then the corresponding slack surplus are 0. In condition 2, it says if the constraints are satisfied as strict inequality, that means slack surplus appear in the basis, then the corresponding original yi's in the dual variable vanishes. We can look for one more example to make this more clear. Let's take, there is one more example. So find the optimal solution of maximize z equal to 2x1 plus x2 subject to x1 plus 2x2 less than or equal to 10, x1 plus x2 less than or equal to 6, x1 minus x2 less than or equal to 2, x1 minus 2x2 less than or equal to 1, and both the variable non-negative. By solving its dual. So we want to solve its dual and then we want to find the solution of the given problem. Use complementary slackness condition to write the optimal solution of primal. Now on this side I am writing the dual of this. So let's say this is my primal problem and on this side I am writing my dual problem. So what is the dual of this primal problem is? It is minimization of y, which is 10y1 plus 6y2 plus 2y3 plus y4 subject to y1 plus y2 plus y3 plus y4 greater than or equal to 2, 2y1 plus y2 minus y3 minus 2y4 greater than or equal to 1, and all the yi's are again non-negative. Now because the question says by solving its dual we want to write the solution of the primal, so we will solve dual, and to solve the dual we have used big M method. So I can simply write here the solution optimal table. We solve dual using big M, or you can even apply two-phase method to solve this, because if you solve this problem then you require artificial variables in the dual problem. As you can see that the constraints are greater than 2 and greater than or equal to 1. So there are two constraints and both the constraints require artificial variables, and because we involve artificial variables so we need to use either big M or two-phase method. And let the optimal table is, so once you apply this method you can find the optimal table, and the optimal table here is, so in the basis we get y3 and y2, and here because we are solving the dual problem so I am here writing capital Y. These are all decision variables, and I have involved here the slack variable. I am not writing the artificial variables, but we are solving here. Now we solve here this problem star, so we can say we are solving the problem star, so we solve dual star. Okay, now because these are basic variables so we can write this quantity as 1 0 0, y this is this, and the other columns. So now at this moment we don't require artificial variable columns, so I'm just crossing these entries for the time being, but we can write this as simply negative of these scale surplus variables. So this is half, this is 3 by 2. Now the optimal solution of dual is y minimum is 10 at the complete set of the solution is y1, y2, y3 and y4, and we also have s1 dash and s2 dash. These are the slack variables used in the star problem. So what is this? This is 0, 3 by 2, half, 0, 0, 0. And now to apply the complementary slackness condition, we need to identify which of them are basic variables. So optimal primal solution using complementary slackness conditions is, so for this I need to write x1, x2, and then there are 4 slack variable used in the primal problem. You can see here that in the primal problem there would be 4 slack variable. So one slack variable will be used in this case, in this constraint, one will be used in this constraint, and 2 more in the next 2 constraint. So there will be 4 slack variable used in the primal problem, and then there are 2 original variable x1, x2. So we have this, and we want to now write down the answer of this problem. Now because y2 is a basic variable, and this means my corresponding second decision variable s2 will be 0. y3 is a basic variable, so the corresponding s3 is a 0. So you substitute these values x1, x2, s1. Now s2 is 0, s3 is 0, and we need to know what is s4. Now you know that s2 and s3 are 0. So convert primal constraint into equality. Primal problem constraint into equality, and then solve the reduced system. So now if you see this, what is the primal problem that we had? We have the primal problem maximum of z equal to 2x1 plus x2 subject to x1 plus 2x2 plus s1 equal to 10, x1 plus x2 plus s2 equal to 6, and then we have x1 minus x2 plus s3 equal to 2, and we have x1 minus 2x2 plus s4 equal to 1. Now these two constraint becomes x1 plus x2 equal to 6 and x1 minus x2 equal to 2, because we know that s2 and s3 are 0. So we know s2 and s3 are already 0. So we reduce this to this constraint. Now you can further solve these two and you can find the value for x1 as 4 and x2 as 2. So once you know what is x1, you can substitute x1 and x2. You can find the corresponding value for s1, that comes out to be 2, and s4, that comes out to be 1. So we can find now the whole optimal solution set. So optimal solution of primal is x1, x2, s1, s2, s3, s4. So what is x1? x1 is 4, x2 is 2, s1 2, s2 and s3, they are 0, and this is 1. And if we can substitute this value in the objective function to get what is maximum of z. So the maximum of z is 2 times 4 plus 2, and that's is 10. And this optimal value 10 is same as what we have already obtained, y minimum, and this, they both are same. So here the only thing that needs to again remind you is that complementary slackness condition works only for the basic variable. If the slack variable in either system is 0, that means the corresponding original variable in the other problem vanishes. And if the original variable appear in the basis, then the corresponding slack variable in the opposite system are 0. So you can either solve the given LPP using simplex method or big M, so we know which are the basic variable. But suppose if you're solving a problem with the graphical method, and in that, because we directly do not identify which is basic variable, so let's do an example for that also. So there is an example number 3rd, and this says solve the given LPP with graphical method, and then apply complementary slackness conditions to find optimal solution of dual. Okay, so what is my given LPP? This is minimization of z minus x1 plus 2x2 subject to minus x1 plus 3x2 less than or equal to 10, x1 plus x2 less than or equal to 6, and there is one more constraint, x1 minus x2 less than or equal to 2, and both the decision variables are non-negative. Now suppose I want to solve this problem with the graphical method. So in that case, let me to draw the graph of this, and then I can identify the feasible region feasible region of given constraints. So we can have the feasible regions. We have x1 and we have x2. There are three constraints that needs to be drawn. So the first line, it passes through 0, 10 by 3. And then there would be one more line. This is 2, 0. This point is 0, 0. And then there would be one more constraint that passes through this. So this line is 6, 0. And this point would be 0, 6. So if this is first constraint, this is second constraint, this is third constraint. So here is my constraint number 2. This is constraint number 3. And this is constraint number 4. And this point, I'm call it as O. This is A, B. This is 4, 2. This is C, 2, 4. And this point, let's call this point as D. And the feasible region here is this one, which is highlighted. Now the optimal solution of this problem is, you can either draw the objective function line or you can calculate the objective function minimization z minus x1 plus 2x2 at these corner point, and you can find the optimal solution. So what is the optimal solution here is that value of z, because we want to find minimization, so z minimum is minus 2 at the point 2, 0, which is A. So this is the optimal solution of the given primary problem. Now from here, because the optimal solution exists at A, but it is a corner point, and at this corner point we cannot directly say which is the basic variable and which are the non-basic variable. So we know that what is the complete solution. To find the complete solution, you again convert the given LPP star in the equality system and then substitute x1, x2 in the star to find what is the slack variable. So the complete solution is x1, x2, and then you require 3 slack variable in these 3 constraints. So by substituting x1, x2, which is 2, 0, we can find out what is the value for S1. S1 is nothing but 12, 4, 0. Now this is very clear that because the non-basic variable takes the value 0 and the basic may not take the value 0 unless until they are not degenerate. So these are non-basic variables and these 3 are basic variables in the primal problem. So once we identify which are basic variable, which are non-basic variable, you can apply complementary slackness conditions. Now let's write the dual of the primal problem. What is given? So our dual is minus 10y1 minus 6y2 minus 2y3 subject to y1 minus y2 minus y3 less than or equal to minus 1 minus 3y1 minus y2 plus y3 less than or equal to 2, and we take all the decision variables non-negative. Now what is the dual optimal solution? So for dual optimal solution, again we require y1, y2, y3, and then you require 2 slack variable which are used. And you can see again, because x1 is a basic variable, s1 is a basic variable, and s2 is a basic variable. These are basic variables. So from here we can say, if x1 is a basic variable, so that means my corresponding s1 dash is 0. Because S1 is a basic variable and S2 is a basic variable, so S1 will ensure that Y1 is 0, S2 will ensure that Y2 is 0. So Y1 is 0, Y2 is 0. If Xi's are 0, slack are 0. If Si's are 0, then the original Yi is 0. And now I am remaining only with Y3 and S2 dash. Now you substitute these values equal to 0. Now you substitute these values in this system and you can find out the remaining values of Y3 and S2 dash. So we get this Y3. So we have Y3, S1 dash and we have S2 dash. This is equal to, so we want to substitute and solve. So we get the solution as 0, 0, 1, 0 and 1. And once you know the whole set, you can substitute this in the objective function and you can find out what is the maximum of y, and that turns out to be the same optimal value as we have already obtained in the case of the primal. So they both turn out to be the same. So that's all about the complementary slackness conditions.